Hi everybody, I'm Emily Bywater. I've been taking the lead on this jumping project since the beginning. Today I'm going to talk to you a little more about why we care about jumping exoskeletons and how they work, and I hope that some of you are getting excited to try them on later. So first off, some of you might be familiar with exoskeletons as seen in Hollywood. I have a clip here from the original Iron Man. I also have some images here from The Dark Knight Rises. Bruce Wayne has a knee exoskeleton that helps him after he gets injured. I have the Avatar Way of Water exoskeleton, the Skell suit, and also a picture here of Tom Cruise from the Edge of Tomorrow movies. So while these exoskeletons are super cool, they're not necessarily realistic. They're not something that we're seeing today in research labs and in industry. So today I want to show you some more examples of what's actually going on in the real world outside of Hollywood. All right. So on the left here, there's a picture of the Defy Exoboot, which you're now familiar with from the video. Next to it, I have a picture of the M-Blue exoskeleton, the knee portion of it, that is a product of the Locomotor Systems Lab here in Michigan Robotics. I've also got a picture of a soft exosuit designed in the Harvard Biodesign Lab, and then finally, the Rewalk exoskeleton, which is used to help rehabilitate people after spinal cord injury. So while exoskeletons can be used both for people with disabilities and to augment able-bodied motion, today I'm going to talk to you a lot about augmenting able-bodied motion and specifically how exoskeletons can be used in the workplace. Exoskeletons act in parallel to your muscles, providing assistive torque so that your muscles don't have to exert as much force, which can reduce some of the strain and prevent work-related musculoskeletal disorders. They're mostly prevalent within walking tasks. So to give you an example, I'm going to show some applications here. So exoskeletons can be used by anyone who needs to be on their feet a lot. So firefighters, nurses, or people who work in factory, warehouse, or assembly line jobs may all benefit. But the US Bureau of Labor Statistics has named other actions that might benefit, or I guess other actions that are taxing in the workplace, and we know that these might also benefit from exoskeletons. These can include things like stair climbing, and then also running exoskeletons are becoming more popular. So today we're going to be talking mostly about how we move beyond walking. So to go beyond walking, we're going to need to be able to attack more energy-demanding activities. And right now, there are some limitations to exoskeletons that are preventing us from doing things like taking off with a jetpack like Iron Man does. Some of these limitations include mainly the weight of the exoskeleton. That's a huge barrier. And heavier weights also require a larger power demand. We don't necessarily have the light enough and efficient enough batteries in order to do some of the things that we might want to do, especially when weight is involved. Also, bulk can be a huge issue. So people want to be comfortable in the exoskeletons. We need people to accept them and want to wear them in order for them to be used. So if exoskeletons are bulky, uncomfortable, or have other issues, that can be a problem. And then finally, we have to be able to provide a comprehensive set of instructions with the exoskeleton so that it knows what to do. And that can vary across tasks and also across individuals. And so this is really complicated. And we're working a lot in our lab on how to provide this set of instructions, as are other people around the country, for not just exoskeletons, but other assistive technologies as well. So beyond walking, what I'm mostly going to talk about today are non-steady state activities. Let me first define for you what a steady state activity is. A steady state activity is something like walking or running, something where you're doing the same action over and over within a time span. Perhaps you're doing it on the treadmill, so everything is exactly at the same pace the whole time. But a non-steady state activity is going to be something more like jumping, something that might be explosive or ballistic or change from moment to moment. And so a couple examples of this, one would be manual materials handling. Maybe you work in a warehouse where you're moving boxes from one part of the floor to another, and you're turning and squatting and lifting and placing, and that's a non-steady state activity. Another example would be an agility task. So let's say that you work in security and you have to leap over a barrier to, I don't know, protect whatever building that you're providing security for. That would be another example of a non-steady state application. So we decided to tackle one of the quickest non-steady state activities that we could, a vertical jump, and our goal was to develop a jumping controller for the Defy Exoboot. Now, we hypothesized that we could provide parameterized assistance to get about a 1-inch increase in jump height. And that may not seem very high to most of you. The first thing I'll say is that the jumpers in the competition got 2 inches, but they were specifically chosen to beat Cassidy. So it is possible to get higher than 1 inch, but things like training and athletic ability are going to play into that. The second thing is that in the literature, 1 inch is pretty significant. So if you think about maybe like how high you want to go, like we're not maybe at the 5-inch, 10-inch mark yet. 1 inch is still impressive for where the literature is at today. So let me tell you a little bit about the Defy Exoboot, which is what we chose to accomplish this task. If you're one of the lucky people who got a worksheet to fill out today, you might want to pay attention to some of the parts on this slide. So the Defy Exoboot was designed for walking, and it's been shown to reduce the metabolic cost of walking. Metabolic cost basically means how many calories does it take for you to walk. And this is measured via oxygen consumption and carbon dioxide release, so gas exchange as you're walking. We can easily measure that in the lab on the treadmill. The exoskeleton weighs about 5.5 kilograms. This is split between the strut, which weighs about 1.4 kilograms on each side, the boots, which weigh about 0.7 on each side, and then a waist pack, which holds the batteries, and a computer for controlling the exoskeleton, which is about 1.3. There is a motor and an actuator here in the center of the exoskeleton. The actuator takes the energy of the motor and converts it to motion, which pulls on a belt transmission that actuates a lever arm. So I went through that all pretty fast. Let me sort of use my hand to outline what that means. So imagine that my hand is your foot. The lever arm is going to be pulling the heel of the foot upwards in order to provide torque. So if you're walking, this is happening during the push-off phase, and if you're jumping, this is happening as you lift off the ground. There's also a shin cuff here, and you can feel the torque through the shin cuff as you're jumping. If I was standing here wearing the exoskeletons right now and they had torque being applied and I started to squat down, I would be able to feel resistance against my shins. The max torque that the exoskeleton can apply is about 38 newton meters per side, and that's about a third of the biological ankle torque. So 38 newton meters probably means nothing to most of you, but your ankle can provide about 120 newton meters of torque during walking. So this is about a third of that, which basically means that the exoskeleton is safe. Your ankle will be able to overpower it in any task that you're doing. In addition, there are hard stops and geometric limits on the torque that can be applied, so the exoskeleton will not be able to apply torque past the limits of your range of motion. Finally, for those of you out there who might be interested in batteries, we can get about 100 jumps with the exoskeleton before we're going to have to switch out the batteries. All right, so now I want to talk through the set of instructions that I was describing before. So this is how the controller works. This is how we facilitate jumping. As one prepares to jump, you're going to be standing, preparing to squat down, and we'll have the belts of the exoskeleton spool up. This is a safety measure so that when you jump, we don't have any snapping going on in the belts as they provide a large offset torque to your ankle joint. As one squats down, you'll start to feel an increased amount of torque against your shins in proportion to the ankle angle that you've squatted to. And in the video, we talked a little bit about how this is like compressing a spring. So if you can imagine you're compressing the spring, you're getting ready to release a large amount of energy. In state 2, that's where the energy is applied. This is when you're jumping and lifting off the ground. We let that spring go, and we add work to the jump in order to make you go higher. And then finally, in state 3 of the controller, we have the exoskeleton shut off and the belts unspool. And this is, again, a safety measure so that when you land, there's no torque applied on your ankles anymore. You can see here that I have some ankle angle and ankle angular speed variables outlined in this plot. These are the variables that we tune from individual to individual. So we have sensors on the exoskeleton which are going to measure these, and then we tune these to make the exoskeleton feel right for everybody. So we tune these based mostly off of preference. So we collected data from 19 subjects to see if the exoskeleton was actually working. We tested 10 different conditions. So we had a high torque condition, a low torque condition, a no exoskeleton condition, and we tested those from deep, shallow, and preferred squats, which are outlined here on this slide. And then we also had a condition where people wore the exoskeleton, but there was no power applied, and we only did that from a preferred squat. We randomized the order of these conditions, and then we had each of the subjects in the study train for 30 minutes each so that they could get used to the exoskeleton. And this is how we measured the jump height. So you can see the different phases of the jump here: standing, squatting, jumping, and landing. We've put reflective markers on the body that we can measure with our motion capture camera system. And the little red and green balls that you're seeing attached to the sticks in these pictures are those reflective markers. And then the model builds the body around those. And so we measured the difference between the hip markers during standing and the hip markers at the peak of the jump to determine how high people had jumped. You may also notice the red arrows on this slide, and these are the ground reaction forces. So you can see that as someone squats down, the reaction force increases. When they jump off, they're not on the ground anymore, so we no longer see a ground reaction force. And then there's a huge spike during landing. We saw some pretty awesome results. So this plot is a bar plot that shows the height achieved on average over 5 subjects across the conditions: high torque, low torque, exoskeleton on with no power, and then the self condition with no exoskeleton at all. And then on the other side, we have the deep, shallow, and preferred squats. So across squat conditions, we saw a 7.2% increase in jump height between the self condition and the high torque condition. This is about 3.1 centimeters, which is over our 1-inch hypothesis, so that's pretty exciting. And then we also saw a small decrease between the self condition and the exoskeleton on but not powered condition. That's expected due to its weight. The exoskeleton is basically a dead weight when it's not on. On the other side, you can see there's a significant difference between the deep and preferred squat conditions, but not much of a difference. And something that I'll highlight with that is that previous studies with jumping exoskeletons found that they needed to squat from like a non-biological or non-intuitive squat angle that people weren't really going to be going for without direction. And so because we can get a high jump from the preferred squatting angle, our system is much more intuitive, much better for the user to use. And then also, notice the small decrease between the preferred squat and the shallow squat. If you think about jumping even without an exoskeleton, you're not going to jump as high if you don't squat as low, so that's intuitive as well. So overall, height increased by 7.2%, over 6.4% best in the literature, so that's exciting. And that was with the deep squat condition that was non-intuitive, so it's even better that we were able to get that from a preferred squat depth. So we've shown that a configurable exoskeleton with an individualized controller makes it possible to tackle non-steady state tasks beyond walking, and that's what we set out to do. Stay tuned to our work for the final results and also biomechanical analysis of these. And now we're going to go to a quick live demo. All right, you ready, Senther? All right, so first we're going to calibrate it to Senther, and then we'll have him jump. Ready? Go for it. Awesome. So I don't know, some of you might have been able to hear the torque being applied, but you can also see on these plots how the current spiked as he was jumping up, and that's what we expect to see. So yeah, how many extra inches do you think you got there? We have no idea. This stick is not calibrated for Senther, so yeah, I don't know, but. Oh. All right, next up we're gonna have a panel, and that will be moderated by Dr. Michael Gonzalez, wherever he is.
Check, 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 check. Yes, excellent. All right, I'll vamp while they get the chairs set up. Thank you, Emily, for that fantastic presentation. I think that was a really great primer on just exoskeletons in general and what we can expect. So this panel is going to be a collection of students, faculty, and individual from the field who are going to give us a broader perspective on what goes into exoskeletons and sort of where they are at right now in the field and where that field is going. As Emily said, my name is Dr. Michael Gonzalez. I'm a recently graduated PhD from the robotics program, and I studied sensation in upper limb prosthetic limbs, and I'm also just generally interested in sort of sensation and humans in the sort of robotic control loop. Now, my goal is to help this panel of experts build on the presentation that we saw from Emily in order to provide you all with an excellent background for where Exos came from, what is going on with Exos in the field right now, and sort of what are our limitations in the field and where we're heading in the future of exoskeletons and sort of these assistive wearable robotics. Now, for everyone in the audience, you're all in attendance through that presentation, so you had a little bit of a primer. Let me hear a round of applause again for Emily and her fantastic introduction to the topic. So going down this list of wonderful people that I am sharing the stage with, we've got Dr. Bobby Gregg. He got his PhD in electrical and computer engineering from the University of Illinois at Urbana-Champaign and joined the robotics program in 2019. He's the director of the Locomotor and Control Systems Lab and conducts research on control mechanics of biped locomotion. Next, we have Eva Mungai, who's pursuing her PhD in mechanical engineering that she hopes to finish pretty soon. She's on the path. The end is in sight. Her research focuses on control theory, biped locomotion, and the challenges involved in a biped robot doing these transitionary tasks that are not steady state, so things like transitioning from sitting to standing and vice versa. Next, we have Emily Bywater, who obviously gave us that fantastic presentation. She's also pursuing a PhD in mechanical engineering and studied sports biomechanics and occupational exoskeletons, and was a big part of this project that you all saw for the jumping exoskeleton. Next, we have Dr. Elliot Rouse, who got his PhD in bioengineering and biomedical engineering from Northwestern University. He joined the robotics program all the way back in 2017, so he's been with us for a nice long while. He's the director of the Neurobionics Lab and works to understand and quantify the properties of human joints during locomotion and then apply those properties to wearable robotics. And then finally, last but not least, we have Dr. Luke Mooney, who did his PhD in mechanical engineering at MIT, where he sort of developed the seed that turned into Defy Incorporated. And Defy is a robotics startup that utilizes practical, hands-on approaches to design, build, and evaluate exoskeletons for human augmentation. So with all of those introductions out of the way, we'll jump into some questions. So Emily gave us some great sci-fi inspirations for the future of exos, but part of the testing lab is trying to sort of look at this full arc of a given technology. So what are some examples of early exoskeletons and sort of where did exoskeletons come on the scene?
Real life.
In real life, we're in real life now.
Well, I think the first ones I saw were these giant industrial exoskeletons from probably the 80s or 90s. Even earlier. Wow. Yeah, that's right. And they were used for hauling giant pieces of equipment in industrial settings, warehouses, that kind of thing. So really kind of like what you would imagine from the movie Aliens, where we had the hero of the movie, fighting the alien in this giant industrial exoskeleton. It looked kind of like that.
Sure. All right. So basically a forklift on two legs. We're in that sort of range.
And maybe I can add to that. I would say the U.S. government decided to invest in exoskeletons back in the 60s. And there was a big research program around, created some exoskeletons, and they were hideous and really difficult to use. But they had started the investigation into these types of systems. That didn't go the way they wanted it to, and it was largely quiet for like the next 30 years. So not a lot of development. But then as technology progressed, especially embedded systems and computing power, sort of society refocused on it. And I'd say maybe over the last 10 years, there's been this big boost by the US government, the military, and that created some of the work and even some of the trainees that have become people like Fabia and Luke. So now we're kind of seeing what maybe exoskeletons can do now, again.
Yeah, and I think that is a great transition into sort of this next point. So we started with these forklifts on two legs, and there's a lot of development and energy and interest that went into exoskeletons. Were there any advances in the technology that allowed us to sort of miniaturize and actually put them on people, get them into homes and labs? Or was it just, hey, we needed to spend a lot of time thinking about the problem?
Yeah, I'll take this one. So I think the shift in mentality was thinking about building exoskeletons the same way we build any other tool. And that's, let's build it for a purpose, to solve some problem we have. Whereas for a long time, exoskeletons had been, let's build an exoskeleton. I don't know what I want to do with it, but I want to build an exoskeleton. And it turns out when you do that, they're not very useful. So modern exoskeletons are more like external muscles that are being added to the body, or they're used to help with a very specific lifting task, and they've been very successful. So it comes back to user requirements and developing for those.
Sure, yes. Definitely important to have the user in mind. So we have two students on the panel who have run research studies and do a lot of thinking about exoskeletons on people. Emily, your study had 19 individuals that were wearing an exoskeleton. So for the two students, what are the safety sort of considerations for putting these wearable robots on people? We're taking big motors, we're taking big pieces of metal, and we're strapping them to relatively soft human bodies. How are we sort of thinking about how to mitigate some of those risks?
Yeah, I can take that one. Is this on still? I think so. So I talked a little bit about that in the presentation. We have the torque limits at the range of motion. We also have soft limits on the torque within the code. And then the exoskeleton can't apply a torque that will overpower your ankle in the first place. So there are those three things. But then also in the lab, we have a crash mat that we usually put behind people when they're jumping in case they stumble and fall. We also go through a rigorous training process, and we build up the torque from a low torque to a high torque setting so that they can get used to it. I think those are two of the other main things that we do to think about safety.
Can you hear me? Cool. So the other thing that I would add for the particular exoskeleton that I work on, it's a little bit different. So my exo is, it's called Atollant. It was built by Wondercraft, and it's essentially, if y'all have seen Digit or any sort of humanoid robot, it's fully actuated, so you can imagine somebody attaching yourself to Digit. Now, if you've seen the Atlas robot from Boston Dynamics and the way it does this somersaults, right, it has a lot of torque, right? So one other thing that we have to think about in terms of these motions that we do is what's the stability guarantees, right? The control algorithms that we put in there, we don't want to hurt the person, right? So how fast are we going? So there's two considerations. There's number one in terms of safety, and there's number one in terms of comfort, right? So how fast, what's the jerk, I guess what's the acceleration that's happening there? So yeah, those are the other things that I would add in addition to that, is in terms of your stability, what motions are you trying to have it do, and when all else fails, how do you recover when this exoskeleton fails to do what it needs to do?
So going back a little bit to what Luke was saying, you're designing with the person in mind.
Exactly.
When you're putting this on a person, you're really thinking about how is it moving, how is it going to emulate the way that a person moves so that it's not going off in a different direction, and how are we putting limits so it's not doing anything that a human can't necessarily do or would break the human, and just giving that little bit of extra oomph.
Yeah, a little bit of extra oomph, or I guess for people who, for instance, who have, cannot use their limbs anymore, in terms of how can we assist while, still not breaking anything else. So you don't want the exo to make your knee go backwards.
Sure.
Painful.
So, we have these interesting research studies that are involved in, seeing what we can add to human performance with these exoskeletons. What does the pipeline look like for getting from the research space to actually getting these in the hands or on the legs of individuals sort of out in the general community? So for Bobby, for Elliot, for Luke, so people on the sort of research, and then on the sort of industry and actually manufacturing side of these things, what does that translation pipeline look like?
We're still figuring it out.
Right. A work in progress.
Yeah, no, it's a great question. So being in a research laboratory is great because you get to control the environment. You get to pick your subjects, control what conditions they're using the system in, and measure what you're trying to measure. In the real world, you don't get to do that. So you have to build all sorts of safeties and reliabilities and be able to predict how any user might use it. Even someone using it in the wrong way, you still need to be safe. And so that's a huge barrier for us and for really any robotics, any kind of mass-produced robotics. And that gets to the last part, which is cost. Like, our dream is that these devices are a few $100s. Today, they're tens of thousands, hundreds of thousands of dollars, but there's no reason they should be. And so getting to that is the next step.
And if I could just add that there's also, for medical applications, there's usually intermediary step where we do clinical trials in a lab setting before we go out in the real world. And clinical trials can also be done in the real world as well, like take-home trials with a new device. But what we do in this lab right there is we bring in patient populations to try our devices, our control methods in a very well-controlled setting. And if we can show efficacy in this well-controlled environment, that's the first step to bringing it out into the real world. And then also potentially getting the interest of a commercial partner to bring it to market, right?
Yeah, maybe that sounds, I agree with everything that was said. And I would say like maybe two things. One is questions that we're asking kind of in my laboratory and there is, what is the experience of wearing an exoskeleton, and how is it helping someone, and what does it feel like? And we actually let the users kind of tune the control strategy themselves in certain cases to study what people actually want, their preferences. So I would say, like, in addition to these concepts that we're talking about here, like, we would start the question in a way that says, like, what we want it to, we need to learn what we want it to achieve and how it feels first. And then the second thing I would say that's kind of critical to getting out of the lab is not to test in only laboratory conditions. And this is something that the field struggles with. We almost always test on a treadmill at a fixed gait speed, and that shortcuts a lot of potential challenges of getting out of the lab and testing on uneven ground or where you don't have a power supply that you could tether to. So
just a quick show of hands. Who here only exclusively walked on flat ground today? All right, so yeah, so there we go. So important considerations for the research. But we have to start somewhere, right?
Definitely, absolutely.
So, I'll pitch this back to the students, but definitely anyone can sort of hop in. What are some of the questions in this space that you are interested in exploring? Even if you're not necessarily exploring them right now, what are some things where you're like, can we do X with an exoskeleton? Or we still don't really know why, and I really want to dig into it.
Mm-hmm. I think a big one is coupling different tasks together. And I know that a lot of people are working on that, but that's a really interesting one to me. Another thing is, Elliot kind of touched on this a little bit, but quantifying, determining what metrics are best for determining whether an exoskeleton is successful. And there are a lot of people, in our lab included, working on that too.
I'd say for me, the biggest question is in terms of user comfort. What are the metrics you can use to actually tell that this exoskeleton is comfortable for the user? Because one person's comfort level is not the same as the other person's comfort level. So what does that look like? And the other thing that I would say, related to what Emily was saying, is in terms of how do you seamlessly transition from one task to another, right? So when you take a look at different exoskeletons, how does the user interact with that exoskeleton, right? Are they using a joystick? Or is there something on the stick, How is that communication happening? And I think the other thing that would be interesting is, especially when we're thinking about deploying these exoskeletons to the real world, what do you do in the event of a failure, right? Now, crazy idea, when I was thinking about this today, I was like, well, you could have an airbag just deploy, But yeah, what do you do in the case of a failure? Because the whole point of these exoskeletons are to either assist or to, enable people to do more than they can do. But we can't control anything out in the real world, so what do you do?
It goes back to what we were saying earlier. They're almost like wearable vehicles in some capacity.
Hence the airbag, right? So in a vehicle, you get into an accident, boom.
I mean, hey, there's some seatbelt action going on to make sure you're in that snugly.
Yes, exactly.
So we do have an audience question that was submitted in advance, and this is from Augie, who is 7 years old. So this goes out to anyone on the panel. Can they make me jump really high? And maybe Augie didn't see the demonstration earlier. So yeah, how, beyond maybe to Augie's question of really high, how are the current state of exoskeletons for that sort of augmentation and pushing forward human performance sort of beyond that sort of average level?
Yeah, great question. I'll start with the really high part. If you're 7, you're pretty lightweight. We probably could make you go pretty high. But that wouldn't necessarily be safe. So there's that. But then to the second part of the question, we're pushing these exoskeletons to their limits right now. And I think, like, in order to go higher, we'd have to have a different motor, we'd have to have higher limits in some way, but right now we're pushing the hardware as far as we can get.
Yeah, and so that's a great point. So, to Luke, what are as someone who is trying to evaluate and commercialize these things, what are the limits? Like, what stops you from doing more?
Yeah, that's a good question. So the first one is if we build an exoskeleton to jump, it could be really good at jumping. It just might not be good at anything else. And so
Luke, you took my next question. But continue.
So if you want to jump all day, let me know and we'll come up with something for you. But some of the limitations are pretty fundamental that we all face every day. Batteries, motor sizes, the trade-off between mass and power. It's kind of your traditional robotics problems for sure. But in terms of where I think we could go for a specifically designed product, I've been saying from day one I want to dunk a basketball, and I'm pretty far from dunking a basketball. So I think we're looking, 10, 12 inches. And
yeah, I was going to say, how many more inches?
I'm pretty sure I was promised that, right? If I give you the hardware, you'll do the controls?
You can put it on and try.
and from your perspective, Bobby, what do you think are some of the, hurdles to figuratively jump?
So yeah, the idea of an exoskeleton that can do more than one thing is really important, and it's not just the design. It is the design, of course, but it's also the control of what's the artificial intelligence behind the device that allows the user to do a variety of different things. There's a lot of different ways that we can control these things, from trying to infer intent about what the person's doing from one second to the next. That has its own challenges because you can never perfectly infer intent. And then there's other approaches where you can try to avoid inferring intent entirely and just do something that is kind of universally helpful, like compensating for a part of gravity, so that maybe you feel like you're walking in a lower gravity environment, or maybe you feel like you're 30% lighter. That'd be nice, right?
Can I get a raise of hands for who would like to feel 30% lighter?
Yeah, so that's some of the work that my lab is actually heavily invested in. But you had asked a question earlier about what is the current capability of augmenting human performance, and I have another example beyond jumping. And imagine lifting, lowering, and carrying heavy objects, maybe in an industrial setting or a warehouse setting or munitions handling. We actually just recently completed a clinical trial where we were able to increase lifting and lowering capacity by 50% after a person fatigues by using a knee exoskeleton. So they're able to go 50% longer after they've fatigued themselves through this repetitive lifting and lowering. And they could also carry the heavy object over a multi-activity obstacle course as well.
And so in a study like that, are you taking someone to fatigue and then putting the exoskeleton on them?
Okay, so we turn off the exoskeleton. They're wearing the exoskeleton. We turn it off. And so they do the...
That doesn't sound very helpful, Bobby.
Right, it doesn't. But then they fatigue naturally that way. And then as soon as they declare that they're fatigued, then we activate the exoskeleton and see, can they go further now with that help? And they can, about 50% further.
Very cool. Very, very cool. And so, if it was on the whole time, the thought is also they're not going to fatigue as quickly, or maybe they can do their job without fatiguing at all, perhaps.
Exactly, yeah. We want to prevent fatigue and prevent the risky compensations that occur when you fatigue. So, for example, as your quadriceps fatigue in the workplace when you're lifting and lowering, you tend to compensate by lifting with your back. And that's how workplace injuries happen. So if we can prevent that fatigue-induced compensation, maybe we can prevent workplace injuries.
So you brought up a buzzword earlier. You mentioned artificial intelligence, and obviously as a robotics department and in the testing lab, part of what we want to do is sort of address concerns from the community of where technology is headed. Now, I don't think the worst thing that a bunch of exoskeletons can do is maybe get up and walk away, which is not particularly the worst thing in the world. But how do you all think about sort of the ethics around, hey, exoskeletons being used in sort of military functions? How do you think about them being used in terms of having people over-rely on exoskeletons and not getting sort of the rehabilitation that they would get if they were walking under their own weight? What are some of those ethical sort of quandaries that you think this field might need to navigate? Sorry, big question. Elliot, take it away.
I would say maybe I'm going to stay away from the ethics side. But one of the major questions would be if we give someone an exoskeleton, let's say you want to increase the mobility of elderly adults. We give that an exoskeleton, we expect them to go into the world and make their life better. You might think, okay, we're reducing the amount of effort that their muscles have to provide. Their muscles could atrophy, like that's cardiovascularly maybe not helping them. And so that's on one side of the scale. We don't actually know the answer to this, what would happen. But on the other side of the scale, and personally what I would hope is that with improved functionality, people get out into the world more and actually do more, as opposed to keeping what they're doing, their activities the same and just lowering their effort. And that's still an open question. We don't actually know if we gave exoskeletons to people that it would improve their mobility or improve their health if it improves their mobility.
All right, we didn't get into what happens if we give them AI or to the military, but maybe we'll save that for another time. That is all the time we have for this panel, so thank you all so much for giving us a little bit of information on where Exos started, where they are now, some of the questions that we still have. Everyone make sure you stay around for pizza and to see some of the Exos sort of in action, poke around, and definitely find our panelists or myself. We all have these yellow name plaques to ask us questions because we're here to answer your questions and sort of have this engagement as part of a bigger robotics community. So give a big round of applause for our panelists here. Thank you for the organizers. Thank you for the department and this fantastic building. Yeah, all right.